Oh, hi, it's me again. Really cool that my program stopped working. And I stopped paying attention. I think I got lulled into a false sense of security because it got past the time when it normally craps out of me. But hey, I did this entire problem, number three, and I did this entire problem, number one, and oh my god, I did this entire problem too, and this entire problem. This is where I crapped out. So I crapped out. You guys missed four whole problems while I was just sitting here talking to myself. I'm not redoing them. Sorry, kids. Not redoing them. I'm tired. I don't want to. Here's your rows. I think you heard me explain this one in the video. Probably. Let me go check on that. So no, you didn't even get to hear me do this one. Because before I did this one, I was talking about what it would look like if it was cosine. So actually, when the video craps out, the graph you're seeing is still the one for cosine. So my conscience feels a little guilty that I'm going to shortchange you guys out of 5 problems. So maybe I'll give you the super fast version. I don't have the heart. I don't have it in me. I don't want to. Oh, I can't redo it all. Okay, we're doing it all. Somebody better say thank you to me after all this. Okay, so how do you do this one, kids? Well, I think I told you, at least I was trying to tell you, that for cosine, you heard me say, that cosine always has its first pedal just symmetric to the x-axis. If it's a positive coefficient, then it's right on the positive half of the x-axis. If it's a negative coefficient, then it's right on the negative half of the x-axis. Sine, on the other hand, its first pedal rotates by whatever the increment of the sinusoid is. I think I'm safe saying that. I should probably double check that that's true though. But if you take 360 divided by 3, that gives you your period. If you take your period and divide by 4, that's the increment, right? And then lo and behold, our first little pedal, it's not at 30 degrees because we had a negative coefficient. So negative 30 degrees though, you can count on that as your first axis of symmetry for your first pedal. Then also, because there's only 3 pedals, of course every subsequent pedal would be 120 degrees away. So from negative 30, 120 says there'll be another pedal at 90, 120 says there'll be another one at 210, and there's only 3, so at that point you're done. With a sine function, you're starting on the pole, and you're with a negative coefficient, your radii are getting, well, they're negative and getting more and more negative. You can see that in this graph here. So if we're starting at the pole, then this is actually the first bit of our trip, is we're actually graphing the top half of this leaf. So did I lie to you then? Because this ain't our first leaf, but it is correct. I might have to modify what I said about the increment. Anyway, there you go. No, I don't have to modify anything. I was right. We would be symmetric over the 30-degree line, but our radii are negative. So don't rotate negative. Project it to the other side. Yeah, maybe I'm glad the video stopped because I explained it badly before. 30 for sure is the radius around which we should have our first pedal. But because the coefficient is negative, it won't be here at 30. It would be across the way on the 210. But that's what's going to happen. As you graph this thing, you go da 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 da, and then you go around here and up and up and up and up, and then down and down and down. And then finally around that guy and back in. But that's it. That's how you got this graph. The coefficient of 4, of course, means that the petals all have lengths of 4. I don't know. I feel like I'm rambling, but that's how you do roses. How about you ask me Tuesday if you still have confusion about roses? Okay. Next. Here's a cardioid. I'm just going to take it from the top. I'm just going to take my lumps. And I'm going to keep a better view on my program, which is still recording. 440, 442, 443. All right. So how do you do this? You're supposed to be recognizing that this is certainly a limacon, just by the form of it. It's an A minus B cosine theta. So that's the right form for sure. then they're both 3's, so they're equal, so that makes it a cardioid. And again, this A value, it's really the D value of a sinusoid. It's the midline, so go up 3, make a midline. But then with an amplitude of 3, you know that you get a max at 6 and a min at 0. It's the fact that we have a min at 0 that tells us we're a cardioid, because we'd run into the pole, but we wouldn't get that inner loop from negative values. And because it's 0 and not just like 1 or something, we don't get a dimple. We don't stop short of the pole. We really do go all the way to the pole. So there. Cosine would start at its max, but it's a negative cosine, so we actually start at that min at 0 and rotate up. So we'll go to the midline, to the max, to the midline, to the min. I can just plot these points now. So at 0 was 0. We start right on the pole. Then at 90 degrees we're at 3. So 1, 2, 3. Then at 180 degrees we're at 6, which is way over here. Then at 270 we're at 3 again. And by the time we get to 360, we've come back into the pole. All right. Now, just in terms of making a good-looking graph, I was trying to make this argument about, if you pictured a rectangle here, you certainly don't want your graph to fit inside there. And you don't even want your graph to be close. Like some people are like, brrr, and then it's just, brrr, and no. Even if you do kind of bump out. Like this is too skinny. I'm talking about this rectangle because I want you to know you should be coming sort of generously high above that rectangle. Coming down through this point, at that point you should be almost vertical. And you're falling down, you come way below that rectangle, hit that point, go way to the right of it. And that's going to be a much better looking graph. So this first guy that I made was crap. And you can see this guy's much rounder. This is more what you want to see. So again, make sure you're going well to the right of this point to get that good shape over there. You're going well above this part to get that good round shape. And don't go to the left of this at all. Remember, this is of course our maximum radius, so you won't go to the left of that. But you will be coming down through it smoothly, not too sharply. If you're coming in there at an angle and making like sort of a classic heart shape, by classic heart shape I mean this, where it comes down and it's sharp at the bottom, that's not right. You need to be coming in and be pretty well rounded off, like that. Okay, but that's it, moving on. And I did this whole one too. Ideally, you are looking at this equation and you know that because it's just a sine theta, it's a circle. Because it's sine of theta, it passes through the origin and has the y-axis as an axis of symmetry. So that means you're bumping your other points up from there. So that 5 halves tells me my diameter is 5 halves. I just didn't feel like going to 2.5 because that's ugly. So I changed the scale. We said that's not 1 anymore, this is 1. That's not 3. This is 2 instead of 4. This is not 5. This is 3 instead of 6. And with that scale, I just have a better looking graph because now I can plot my point at 0, 0, plot my point here at 5, the middle being here, and then these points I just roughed in. Just make sure that you're going about as far up and down as you are left and right, and then just make your circle. That's it. Good enough. Alright, I did an entire systems problem. So what did we say? We said that you've already got 2 equations that are both solved for r. So of course you're just going to take this r expression and plug it in for r here. That's why you get negative 3 equals 3 cosine 2 theta. Divide by 3 and you get negative 1. And you know that cosine equals negative 1 only here at pi, right? So that must mean that 2 theta is pi plus 2 pi k. So to solve for theta, you just multiply through by a half, and you get pi over 2 plus 1 pi k, which tells you that your 2 solutions on the unit circle are pi over 2 and 3 pi over 2. But again, I don't really want just theta. Your solutions to a system should be ordered pairs. So you should be giving me the complete list of points, r comma theta. And the only r value that satisfies these equations is negative 3. So you know right away that the r will be -3 with the pi over 2 and -3 with the 3 pi over 2. And then lastly, you're supposed to graph the two equations together and mark the solution points versus the common points. So graphing r equals -3 was a piece of cake because it's just literally a circle with radius 3. So the red guy's easy. Then the other guy was this. Oh, I can't move it. 3 cosine 2 theta. The 2 there tells you that we're talking about a rose. We're talking about 4 petals, because when this number is even, you double it to find the number of petals. And every petal has a radius of 3. We also know that because we're cosine, our first petal will be symmetric over the x-axis. So I knew I could go out a distance of 3. And then 90 degrees later, 3. 90 degrees later, 3. 90 degrees later, 3. And I'd get these 4 petals that just ran around. So cosine is going to start here, and as we rotate, getting positive radii that are getting bigger. I guess we're going to travel this branch first. So we're going to come around, then come back in, and go up, and come back down, then run over here, then come back around, then go down to there, then go back up to there. I think that's right. I think that's the right pattern. Anyway, you see we get the 4 points of intersection all around the circle. But if you recall, our solutions were only at pi over 2 and 3 pi over 2. That's why this point is marked as a solution, and this point is marked as a solution. These points are simply common points. And the reason they're common points is because if you imagined a ball spinning around the red graph, remember that was a negative radius. So at 0, we weren't getting this point. We had a negative radius. We were getting that point. And if you imagine a blue ball, for our cosine function at 0, we were starting right at our max, which was 3. So that ball was here. So those points weren't together there. And then as we run around the circle, this point ran down to here. And this point, what did it do? I don't know anymore. As we went that away. Yeah, we must have followed this path. Yeah, that's right. So this 45 degrees or whatever, and then 90 plopped us there. And so we did crash into this guy, because as he rotated 90, he was going under there too. So the two balls did meet here at the same time. So that was a solution. Then the blue ball went la-da-da over to there, while this guy went D-to-D over to there. And again, they were across from each other rather than meeting at the same time. This guy went up to there, and this guy went I've lost track. Oh yeah, and then up, and then slam. I'm not going to do this forever. In fact, I'm done right now. There's a difference between common points and solutions, and I just explained it to you. Moving on. Hey, look, it's another problem that I already did while the computer wasn't paying attention. So let's look at how this one went. We took the two r expressions and set them equal. I added 3 sine to get 6 sine. I divided by 6 to get a half. And at that point I knew when sine was a half, because I know my unit circle. Sine is a y value, and y values are a half at 30-degree reference angles here and here. So that told me I wanted pi over 6, and I wanted 5 pi over 6 plus 2 pi k. So that meant if I'm limiting my thetas to just the first trip around the unit circle, then my particular solution is just those 2 theta values. And again, you do need to give me ordered pairs. So taking pi over 6 and plugging it back in, what's the sine of pi over 6? Isn't it a half? Wasn't that the whole point? Is that we were solving for the thetas that make sine a half? So obviously when sine is a half, you're getting a radius of 3 halves. So we got 3 halves pi over 6 and 3 halves 5 pi over 6. So I've got a lot of things in a box over here, but the one true answer to this question is this box. Because the solution to a system of equations is supposed to be ordered pairs, right? So you should be giving me your answer as the set of ordered pairs, r comma theta, and it's just those two. Then you gotta graph these things together. So 3 sine theta is a circle of diameter 3, centered somewhere on the y-axis and shifted up. So I'm roughing that thing in. This guy's a cardioid. The y-axis is its axis of symmetry. Sine starts on its midline. right? Center on the midline. Yeah, and the midline's 3. So it's 0, we're getting the point 3. Then it's negative sine, so from the midline we're decreasing down to our min. I can't do this anymore. Which would be 0? I don't know. I'm losing myself. Where's my sketch? It's right here. So we started on the midline, decreased down to 0. So we started here, then we got pulled into the pole. Then from the pole we increased back out to 3. Then from there we increased to our maximum of 6. To there. And then finally from there we decreased back to the midline value of 3. So anyway, at the time, I zoomed way in on this. And we see our 3 points of intersection. They are here and here, and the pole. Algebraically, our only 2 solutions were coming at pi over 6 and 5 pi over 6. So that means this point at the pole must be a common point, not an actual solution, whereas these 2 points are solutions. See how they're labeled with little tiny baby s's? That's because at the time I was zoomed way in at like 400%. So that tiny s didn't look so tiny when I was zoomed in on it. Infuriating. All right, let's do 5 together, and then what? Then we're done. Oh, cool. So I had almost finished when my computer, or when I realized my computer had crapped out. All right, this is going to be the same diff. Same deal. Just take this guy, plug it in. You get 6 sine theta. It'll be equal to 5 sine of 2 theta. And to solve this guy, you're pretty much going to have to use the double angle identity. So it's like that. So you now have 6 sine theta equals 10 sine theta, cosine theta. The temptation to divide by sine theta, I bet that's pretty great, and just cancel them out. You better resist that urge, because you'll lose solutions if you do that. Instead, subtract this from both sides. So you get 6 sine theta minus 10 sine theta cosine theta. Oh boy. Cool. And that'll equal 0, and that's a theta. So I can actually factor out 2 sine theta to be left with 3 minus 5 cosine. And that equals 0. So it's at this point that you recognize you've got one factor and a second factor, and they both equal 0. So you can use the 0 product property to say that when 2 sine theta equals 0, that's going to generate some solutions. And when 3 minus 5 cosine theta equals 0, that's going to generate more solutions. So divide by 2 here and you get sine theta equals 0. Unit circle says that sine theta will only be 0 here and here. So that's giving us solutions of 0 and pi. Now the next part's tricky because you're going to add 5 cosine theta to both sides. You're going to divide by 5, and what you get is 3/5. And cosine can equal 3/5, but they're not unit circle values. X would equal 3/5, what, like here and here? And so I don't actually know this angle measure, but I can find it. I know that theta would just be the inverse cosine of 3/5. And you could give that as your answer, and you can tell by the symmetry of the unit circle that theta is going to be plus or minus those. So that's giving us 2 more solutions. It's giving us positive cosine da 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 and negative cosine da da da. So I'm expecting 4 values of theta, which I guess means I'm expecting 4 points of intersection, except that doesn't quite pan out, because when you turn these guys into ordered pairs of the form r comma theta, let's see what we get. First, let's shrink this so you can actually see it again. And let's scroll up too. Or just grab this and bring it down. So the 6 sine theta is the part we should be able to evaluate. At 0, remember sine was 0 there. So 6 sine of 0 is 6 times 0, which is 0. So 0 is giving us the ordered pair 0, 0. And the problem is pi is 2, because the sine of pi is also 0. So pi is generating the same exact point again. 0, 0. Well, it's not 0, 0. I guess technically it's 0 pi. But 0, 0 and 0 pi are the same location in the coordinate plane. So we're not going to end up seeing 4 points of intersection for our 4 solutions, because these 2 points are the same point. We'll only see 3. But let's do the other one now. So the good news is this angle may be ugly, but when we go to plug that in, oh crap, I don't want to explain this again. Alright, here I go. Hey, remember how cosine is 3/5? So remember you could draw a little triangle where cosine is x over r, so it's 3/5. And remember the 3, 4, 5 Pythagorean triple. So maybe you remember how when the cosine of an angle is 3/5, the sine of that same angle is 4/5. Everybody remembers that, right? So whatever theta is, I know that the sine of theta is 4/5, which times 4 or times 6 is 24/5. So my radius is 24/5, and my angle is the inverse cosine of 3/5. Alright, that's cool and all, but there's another one. So what if we were using negative? Then in our little triangle would be down here. And that means sine would now be negative. So we'd be getting a radius of negative 24/5 to go with an angle of negative inverse cosine of 3/5. Okay, I just got invaded by my daughter. But back to work. These are the 4 solutions. Am I going to expect that you can give me answers that are in the form of inverse trig expressions? Nah, I don't think I am. I think you guys can expect these systems to look more like the first few that we did, where the angles were just nice clean unit circle angles like pi over 4 and pi over 6 and whatnot. You know, I still want to hope that you guys can understand how to use these inverse expressions though. Let's do the graphs and then just look at our common point situation and all that. So who were these guys? That first one's looking like a circle to me. And the second, no, the first one is rows. What was I boxing up? That thing? I don't know, whatever. Anyway, the first one's a rows. And of course it's a sine one. The sine ones are the most annoying. Alright, what did I tell you? I told you to go 360 divided by 2. So 180. And then chop that by 4. So 45. So the increment is 45. So that should mean that our first leaf will have its symmetry over 45 degrees. And then this is 2, so there'll be 1 every 4. So there'll be 1 at 3 pi over 4. There'll be another at 5 pi over 4. There'll be another at 7 pi over 4. And they have radii of 5, so 1, 2, 3, 4, 5. So put a point here, put a point here, put a point there, put a point there. So if we're a sine function, we start at the pole. As we rotate, we run out to this guy, come back in. Then where do we go? Down to this guy and back up? around to that guy, back up. That's a pretty badly drawn one, but I don't care. Then the other guy has a circle of diameter 6. It's sine, so it's going to be up. So I'll have a point at the pole, point up here at 6, center at 3, and I'll come around. All right. So like I said, we had 4 points of intersection, but you're only seeing superpsych. We have 4 points in our solution set, but you're only seeing 3 points of intersection. And I already explained it. It's because these 2 points are the same. The ones you can't see, the ones I'm pointing at that you can't see because they're down here because I'm stupid. These ones. 0, 0, and 0, pi. That's just the origin twice. So it's not weird that we got 4 points, but we're only seeing 3 points of intersection. And the good news is you label all of these as S. You're a solution. You're a solution twice, but just mark it as S. You're a solution. You're a solution. The weird news is, I think these 2 points, and actually the origin too, they're technically common points too. There are angle measures where you're not at these points, where they don't meet there at the same time, but other times they do. So I don't think I really care about getting into those semantics though. If a point of intersection is ever a solution, just mark it with an S. The only points we're marking as a CP are points where they seem to cross, but they're never ever there at the same time. I do kind of care enough to try to explain that to you, so hang on 1 second. Okay, I'm back, and here you go. These are the 2 equations, right? 5 sine 2 theta, 6 sine theta. I'm going in degree mode for some reason, but let's watch as this thing animates. Is this big enough? Let's make it bigger. I don't know what you can see. It looks really bad on my screen, but hopefully for y'all it's okay. Anyway, let me take this little rotating arm. So as we rotate, you can see that they were together at the origin, so that's certainly a solution at 0. Then as we rotate out, they do meet there. That 53 degrees-ish, that's not 53, that's the arc cosine, meaning the inverse cosine of 3/5. It's really negative 53.13, blah, 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 but we see that that really is a solution. Then we rotate around, around, around. At 90, notice one of our points is back to the pole. Actually, it isn't. Why? Oh, because I'm at 89. Get to 90. Now, one of our points is back to the pole, but the point on the circle is up here. That's what I meant by, for a certain value of theta, meaning 90, the origin is not a solution for us. It's just a common point. But it is a solution at when theta is 0. Just mark it with an S. Keep rotating. And you see us here, the blue point is now hitting this point, but the red point is way down here at the other end of this leaf. So they're not actually, that's right now it's acting like a common point, not a solution. As I rotate around more and more and more, they meet again in the center. So there's our 0, pi solution. Then we rotate out, and this point is again a common point rather than a solution. But as we rotate around a little bit more, now this point over here is again a solution because they're meeting there at 307. 307, by the way, is the negative inverse cosine angle. It's basically 360 minus the 53. That would give us 307 degrees, wouldn't it? But then we rotate back, and I'm grabbing the wrong thing, and then we're back to the origin. Anyway, you should 100% understand what's happening here if you want to do well in your quiz. So this thing about how the points move together and come together sometimes, but other times they don't. Ask me questions about that Tuesday if you still have them. All right, goodbye, gotta go.